Welcome, my name is Sonehmi and today we will continue DFT that we have studied last time, and in the end we will see how we can convert frequency domain signal again into time domain signal, that is inverse Fourier transform. So let's start with an example. Last time we saw this formula. In this, n is number of samples in time domain. It varies from 0 to n minus 1, and k is the number of samples in a frequency domain. What this capital N is, it is equal to or greater than n the samples in time domain. We were discussing equality, so in this example n is equal to 8. So if we convert this signal that is given here, 1 minus 2 3 1 2 minus 1 2 and 1 into frequency domain, what will happen? Just use this formula to find these values. We have seen in detail how these values come through this formula. Let's have an example. If I want to find x of 0 when k is equal to 0, what will happen? This factor will become 1, and just add these 1 minus 2 plus 3 plus 1 plus 2 minus 1 plus 2 plus 1. So what will be the result? 7. As you can see, I have drawn this circle here, and the partition of this circle depends on n. If it is 2, then we will divide this circle into 2 parts. If it is 4, we will divide this into 4 parts. If it is 8, as in this case, I have divided this circle into 8 parts. So first is 0, angle is 0. Then what will be the result? We have seen this in the previous lecture. It is equal to this one. So when we put theta is equal to 0, this will become 1 because cos 0 is 1 and sin 0 is 0. Similarly, when we put pi by 4, this value will come, and we will put angles again and again, pi by 2, 3 pi by 4, pi, 5 pi by 4, 3 pi by 2. Similarly, why we draw this circle? Because we need these values again and again. So if we draw this circle, it will be easy for us to just pick these values and substitute in this, and we will get answer. So this signal in frequency domain will be like this one, as I have calculated. Now if I want to plot this signal, what I will do, these are complex values, I will take just magnitudes of these values or absolute values of these points. Now I have told you how to calculate magnitude in the last lecture, but a little bit review here. If I want to calculate the magnitude of x of 1, just take the square of real part plus square of imaginary part, add both and take under root. What will be the answer? 1.7321. So I want to plot this signal now. For that, now I have the sampling frequency fs is equal to 16 kilohertz. It will be given, or just suppose it is 16 kilohertz. Now what will be the frequency resolution? You can see it is equal to del f is equal to fs by n here is 8. Now the difference between two frequencies will be 2 kilohertz, because f del f is equal to fs, which is 16k, by n, which is 8, so it will come out to be 2 kilohertz. Now if I want to plot this signal against frequency, this is amplitude and this is frequency, the value will be 1 2 3 4 5 6 7. Just rough plot. Now at 0 it is 7, at 1 it is almost 2, at 5, at 2 it is 5.4, 1.7, 9, it will go up 4, 1.7, it will look like this. Now what will happen if I want to, this is in frequency domain, 2 kilohertz, 4 kilohertz, 6 kilohertz, 8 kilohertz, 10 kilohertz, 12 kilohertz and 14 kilohertz. Now what will happen if I want to filter out the frequencies that are greater than 6 kilohertz? I want to apply the filter of, let's suppose, filter of 6 kilohertz. I just want to pass the frequencies that are below 6 kilohertz are equal to 6 kilohertz. What will happen? I will just make this component 0. Why? Because the maximum frequency occurs at this one. According to Nyquist's theorem, fs should be twice the maximum frequency. So if I want to calculate the maximum frequency, what will be the maximum frequency at this stage? This will be 8 kilohertz, because 16 kilohertz is my sampling frequency, and if I divide this 16 kilohertz by 2, it will come out to be 8 kilohertz. So I want to filter out this frequency. To make this frequency 0, what will happen? Just substitute this 0 here, and now comes inverse Fourier transform. For that we have this formula: x of n is equal to 1 over capital N, that is samples, number of samples, how many samples you have taken. In this case n is equal to 8, and the rest of the formula is same, but the only difference is replace this x of n with x of k and the minus with plus sign. So if I have this sequence in frequency domain, what will be the signal in time domain? Just substitute or use this formula. So if I want to calculate x of 0, k is equal to 0 to 7, x of k e power 0, because n is equal to 0. 1 over 8, just substitute the values of this and x of k. So you can see we can just add up these values. This will cancel out with this one, and this will cancel out with this one, and this complex part will cancel out with this one, and the rest of the values are real one. So you can add these real one values and divide by 8, you will get 1.25. Similarly, calculate other values by just substituting or using this formula. Now, what is the will be the difference when I make this value or frequency 0? When I filter out this frequency, what will be the signal, or what the signal will look like in time domain? I want to plot this again. Now as you can see, in the start I have this signal. When I made x of 4 is equal to 0, I got these values. Now if we compare these values, what is the difference between these two values? As you can see, the consecutive transition or consecutive difference is less than the previous one, as this is 1 and the next one is -2. Here the difference is greater than this one. This is just minus 1.125 and the next value is just 0.8. So the difference is 0.6 as compared to this one. This is 3. Now what will be the graph of these? Start, I have this signal. In the beginning, just this is original x of n when x of 4 is equal to 9, and the other one is just simple. Now you can see that these are very smooth values and these are highly transitive, or there are very high transitions here. Now what we conclude from this one, just write the indexes here. What we conclude from the whole theory or discussion is that the low frequency signals are always smooth, or the low frequencies occurs at smooth values. If we have high transitions, then it means that we have high frequency signal, and high frequencies occurs where the transition is high. So that's it for today. We will continue in the next lecture. Thanks very much.